let us start this afternoon session. So we'll have Marcin Bobieński, who will speak about the model slow, fast, Darboux systems and pseudo-Abelian integrals.
Okay, thank you. So at the very beginning, I would like to say that it's my first time in IMPA and more generally in Brazil. I would like to thank the organizer, Hossein, for opportunity to speak in this nice and famous place and to visit Rio. I will speak. By the way, in your question to Robert Roussari, you said, Hossein, that you like very much concrete equations. So this is precisely the idea of my talk, to provide some very concrete, very explicit example that illustrates some general phenomena that we investigated in our theoretical work. So at the very beginning, I'd like to say that it is a joint work with Michał Nagrodzki. This is my student, Nagrodzki. And as I claimed, it is just an example of explicit example of object that we deal in theoretical way. Just to provide some background, I would like to recall our theoretical result, briefly recall the main idea and the key point. I mean more precisely our common result with Pavao and common result with Pavao and Dmitry Novikov. Just to avoid all technical troubles, technical difficulties, I will deal. So all theorems I will formulate in a first non-trivial case. But nevertheless, it is also interesting case. First non-trivial case, I mean, all of them will be Darboux integrable system, and of course their perturbations with two factors, just two factors. So, first theorem was our result of Paavo, Mardešić, and me. It is about 2010, I do not remember precisely. It deals with perturbation of Darboux integrable system. So as I said, I will present result in first non-trivial case. Nevertheless, it is formulated in much more general settings. Here I will mark exponents. It is A and B. We deal with foliation given by Darboux integrable form plus perturbation, polynomial perturbation, eta, where epsilon is small perturbation parameter, of course, and Darboux integrable form has the form integrating factor times dh over h, where h is of the form p to our a, to power a, q to power b, and integrating factor is just product of these two polynomials. So as it was said many times during this meeting, if we consider closed cycle of this integrable system, gamma of t, so linear in epsilon approximation of displacement function is given by pseudo-Abelian integral that reads gamma of integral over gamma, and the integrating one form is eta over m. Under some generic assumption that I'm not going to state, just I will say that our assumption is that both curves p equals 0, p to our a. So this curve is p equals 0, this curve is q equals 0. We assume that both are smooth, and we have transversal intersection in both points. But I would like to underline one assumption, namely we assume that A and B belong to some neighborhood of neighborhood of some base point A0, B0. And the crucial in this result was that we are away from 0 with A as well as with B. So all results are, so this is A parameter B here, and the crucial is finite distance here from 0. What do we obtain in this theorem? Actually, first statement was not a main result, but key technical proposition, namely that iterated variation with A, B of this integral of t vanishes identically. And the second claim was that the number of isolated zeros of this pseudo-Abelian integrals, I do not write that, I mean isolated zero, is locally bounded. Locally, I just underline that I mean with respect to parameters of h, I mean parameters of this polynomial p, parameters of q, exponents a and b, but remember this assumption that we are away from 0, as well as with respect to, of course, perturbation form eta. It's locally bounded. Okay, let me just very, very briefly provide idea of proof, idea of method we use here. First relation was already mentioned many times during this meeting, in particular on Paavo lecture, as well as Colin Christopher. It is geometric idea of variation. What do I mean by variation with index A and variation with index B? I mean that I adapt this argument of pseudo-Abelian integral in such a way that it is analytic on some transversal to curve P equal, oops, I think I denoted twice the same curve. Analytic on transversal to curve Q equals 0 and P equal 0 respectively. And this argument is very geometric, namely we start with well, our picture as marked there on the blackboard. We have our cycle gamma, and we make a monodromy with respect to parameter, let's say, okay, first B, since it will be easier to make it. So we make a turn around this curve Q equals 0. So after this monodromy, I would put index A also here. We obtain similar picture. We go back to the same piece of cycle that goes close to curve Q equals 0. But as we wind around this curve, so of course it changes a little bit here, and we obtain something like that. And then we take variation. Variation means monodromy A minus identity. We apply this operator just to cycle gamma. This is our gamma. This is monodromy of gamma with index A. And then we apply this difference variation operator to gamma, and we obtain precisely 8-shape curve. Of course, since this piece is the same as at the beginning of operation, so this piece cancels out, and we end up with such shape like this, figure 8 curve. I will denote it by delta with 8 index due to the shape of it. And then, so using this geometric argument, we can easily show that variation on analytic side of the story, analytic variation with index A of our pseudo-Abelian integral is just given by integral along this figure 8 cycle of eta divided by integrating factor m. And essentially, okay, in a more general case, it is a little bit complicated. We need to make a longer iterated variation operator, but here this is essentially the end of the story, since we are infinite distance from this curve q equals 0. So essentially, it means that integral like this is analytic in parameter that is analytic on transversal to p equal 0. So it means that this variation, this integral is analytic in t to power, this was variation with respect to a, so this is analytic in t to power b. And since it is analytic, so variation with respect to this b vanishes. So variation b, variation a of I is identically 0. Let me make a remark here that due to small denominators problem, this point number 1 does not in general imply, due to small denominators problem, it does not imply that pseudo-Abelian integral is just a sum of some analytic function of t to power b and t to power a. That I is just analytic function of t to power a plus another analytic function, t to power b. Nevertheless, on formal level, it is true. And let's say, in model case, we expect that it should be something like that. Okay. I think I will skip the argument how point number 1 implies point number 2. I just say that we use here purely analytic argument, namely so-called argument principle. To estimate number of zeros of pseudo-Abelian integral, we make some, maybe just a small picture. We make a shape like this. We want our aim is to estimate number of zeros of I function here. So due to well-known argument principle, it is enough to estimate increment of argument along this curve. And the key point is that estimation of increment of argument of this analytic function just can be bounded on these two pieces by 0 of this variation, where here is just 2 pi b. Okay, here increment of argument is bounded by number of zeros variation with respect to bi. So the easy induction goes. Okay, so it was the very first result in this direction where we investigated this pseudo-Abelian integral. As I marked here in this point that I've just erased, important assumption was that we are away from 0 with A as well as in B. Sorry? Zeros, yeah. Zeros. Yeah, so in next result I'm going to recall, it was theorem by three of us, Pavao, Dmitry Novikov, and me. we deal with the case where indeed one exponent goes to 0. So this is so-called slow-fast case. We now have omega epsilon, since epsilon is usually treated as slow-fast parameter, so now perturbation parameter I will denote in a different way by delta. Eta is equal to 0. And again, result is more general, but I formulate it in first non-trivial case. So the picture is quite similar. I would like to underline the fact that it is slow-fast. So one exponent is epsilon, and it is very slow. Another is a. So this typical cycle of this integrating part of foliation goes very, very, very close, and then it goes like this. This is now our gamma of t cycle. So again, to set up notation, we have situation quite similar times dh epsilon over h epsilon. H epsilon is just p to power epsilon times q to power a, and integrating factor is, as usual, p times q. So what is, the first point is precisely the same, and actually the reason is that the argument was purely geometric. So just I will repeat this first statement that iterated variation, first variation with respect to a and the second variation with respect to epsilon of I vanishes identically, and the proof is geometric, so precisely this is the same. And the second claim is, again, that the number of isolated zeros of t is locally bounded, but I want to underline that this is bounded up to epsilon, so up to exponent equal 0. So of course, this locally bounded for epsilon from 0 to some epsilon 0, and this is crucial that we are allowed to go up to 0 here. Yeah. Actually, to be honest, it is not in our paper. It is not formulated inside a theorem. It is just a key or geometric proposition. But yeah. And then the proof actually of this point goes like this. I'm not going to repeat it. It really goes in the same way. But to obtain implication from 1 to 2, now we need some additional technical stuff. Since for fixed epsilon, we can repeat line by line previous argument. And to obtain bound up to 0, we need to deal with this singular case as epsilon goes to 0. And in this implication, we use so-called weighted blow-up. Namely, we use blow-up of three-dimensional parameters x, y, epsilon. This is weighted blow up, and here parameters would be one. I will write it in one chart: x, u, and let's say capital E, and the weighted blow up reads x is equal to x, y is x squared u, and epsilon is x squared capital E. And the key point to deduce from 1 to 2, we use the following proposition. this proposition actually describes how foliation behaves with respect to this blow up. So proposition is the following. The foliation, I should define foliation. Now it is not so obvious since we have, of course, foliation given by one form on one hand side, but we have three-dimensional space. So we define foliation by two form, of course, omega epsilon equals 0, but another that epsilon is constant, d epsilon equal 0. And the proposition is that the foliation like this can be extended, or shortly extends, it's analytically to the exceptional divisor pi inverse of 0 and singularities of this extended foliation is located These are located on strict transform of slow curve. Transform slow curve. Slow, I mean p equals 0. P equals 0 and center curve. So, okay, for each value of parameter, for each value of epsilon, we have a point of center, and these centers form a curve. So the picture is the following. We have here this exceptional divisor. Maybe I will draw slow curve with red. So we have strict transform of this red slow curve. And so this is marked by red and by, let's say, blue. I will draw the center curve. It goes more or less like this. And our figure 8 cycle that actually we end up after first variation is a cycle like this. This is our delta 8 cycle. So again, it is in finite distance from slow manifold. We can prove using this weighted blow up method that we can control analytic behavior of integral along figure 8 curve, and in such a way we obtain this bound up to epsilon equal 0. Okay, so this is what I said at the beginning, that I want to recall our theoretical results. Now I'm going to go to example. So, as I said, my aim was to provide a simple example, toy example, to be able to calculate more or less everything in explicit way. Unfortunately, it was not possible to construct, actually I failed in this construction, in such a way to obtain true cycle, but it will be cycle in the sense as it was discussed in Lin's Netto talk, that just we consider some transition map, and cycle means fixed point of displacement map. So our our foliation is given by epsilon, integrable foliation, 1 minus x squared dy minus 2yx dx. Integrating factor is just this 1 minus x squared y, and first integral is just y to power epsilon 1 minus x squared. Just so, of course, this is integrable system with this first integral, and the phase portrait looks in the following way. We have this slow curve y equal 0, and to, let's say fast, this is x equal minus 1 and x equal plus 1. And we can consider transversal here for y equal 1 and display, I should draw like this, almost to this slow manifold, and it goes like this. So this curve, to be consistent with previous result, I will mark in orange, and this is our gamma of t. Here I can provide parameterization of transversal, namely that x here is minus 1 plus xi, and here 1 minus xi, and in parameter xi, not epsilon. And displacement holonomy map with this epsilon parameter of xi is just, with dot maybe, is just identity. So this is our toy integrable case. Now we consider polynomial perturbation of this guy. So foliation given by omega epsilon plus delta eta, where eta, and actually I do not deal with arbitrary polynomial perturbation. As I said, I need example where everything could be calculated up to the very end. This is polynomial of x and y, and this is just one form proportional to the x, and foliation is given by stuff like this. So we can consider displacement map like this with additional parameter, with this perturbation parameter delta, and as usual, linear in delta term of this displacement map is just given by pseudo-Abelian integral. So delta epsilon, and let's say delta, okay, is just given by identity plus delta times, and here we have gamma epsilon of p dx over y 1 minus x squared, and this is, well, this integration goes along gamma of t. Yep. Okay, so first theorem would be the following, that we can calculate this pseudo-Abelian integral in this case. One more remark. We will change a little bit parameterization. Namely, we parameterize this cycle gamma of t by intersection point with line x equals 0. So with parameter here we have coordinate y. So essentially, we will parameterize this by y. So theorem 1 is the following. Some expression for pseudo-Abelian integral. And it is given in the following way. This is J epsilon. I want to detach this term by some reason. Plus R of y, and plus the last term is proportional to epsilon. It is g of y to power epsilon, actually. And we can write down formulas for each term. I epsilon of y is just given by the following formula: constant log 1 minus u over 1 plus u. I will say in a moment who is u, plus u times q of u, where q is polynomial of the, maybe I will erase this blackboard. Where q is polynomial of degree less or equal n minus 3 over 2, where n is, of course, degree of p. So n is degree of p. This n will appear in many places. So this is first summand. The second one is R of y, that is polynomial just. Y is a polynomial of degree less or equal than n minus 1. And finally, the function g, we have the following formula for function g. Okay, I put it here, y to power epsilon argument. So just function g is a finite sum from j equal 0 to n, or to maybe n plus 1. Okay, let me write it. N, here some coefficient cj, g of z. So this is some coefficient. Here we have 1 minus z to power j minus plus 1/2, and hypergeometric function with some coefficients related to j and a. I'm not going. The formula is not very complicated. It's not very easy, and z argument. So this is quite compact formula in this case for pseudo-Abelian integral. But there's one more reason why I was particularly interested in slow-fast case, since one can formulate similar example without this epsilon that is small. Just we can construct even easier toy model with just 2 exponents where both are distinct from 0. But there is one more nice remark, namely, as probably everybody knows, for slow-fast system there is well-known and investigated by Dumortier and Durosari another tool for studying Canard-type limit cycles, namely so-called divergence, slow-fast divergence integral. And important remark is that this first term, this j epsilon function, is precisely Dumortier-Durosari slow-fast divergent integral. Remark, this j epsilon is Dumortier-Durosari divergence, slow-fast divergence integral. Okay, so as we have formula like this, so we can formulate now some theorem where we obtain explicit upper bound for the number of zeros of this toy model pseudo-Abelian integral, and it is theorem number 2, namely, for sufficiently small epsilon, here we turn on this slow fast notion. Small epsilon. I would mark it like this. I want to be positive and sufficiently slow. The number of zeros of this Dumortier-Ussari, so first statement, of y such that slow fast divergence integral is 0 is bounded by integral part of n plus 1 over 2 plus 1. And the second statement is the bound for the number of zeros of just full pseudo-Abelian integral. Number of zeros of pseudo-Abelian integral, isolated of course, is bounded by integral part n plus 1 over 2 plus n plus 2. So how do we prove this? And we can create, it seems to me, quite nice picture related to this calculation. So I prepare full blackboard. So here I will repeat this. No, I need more space. This, like this. So first idea of proof. First point is easy since this J epsilon is given in explicit way. Oops, I think I haven't wrote what is. Okay, sorry, I must make one step back. I wrote here that the argument of this J epsilon was some u function, and I did not wrote who is u. And u is just 1 minus epsilon, y to power epsilon to power 1/2. This is parameter like this. And as we know this, so it is good place to make a second remark. This first, maybe here is first remark. So here I can write remark 2, namely that this is toy model of this slow fast Darboux. In general, we have iterated variation equals 0, but here we know more, that this pseudo-Abelian integral is a sum of some function of y plus some function of y to power epsilon. So of course, in this case, this iterated variation follows in trivial way. Okay, so this was this was this step back. Now concerning proof, so if we just calculate derivative of this function j, so it is, we have formula 1 minus u squared, derivative with respect to u. And here we And here we have polynomial of degree less or equal n minus n plus 1, yeah, precisely of this degree. Okay, I will just write that it is polynomial of u of degree less or equal than n minus 1 over 2. But this is derivative, so by usual Rolle argument, it means that number of zeros of just j epsilon function is bounded by this. No. So it should be plus 1. So. And plus 1 we obtain from Rolle. So first point is trivial, and to obtain second point, we observe first thing that our form of pseudo-Abelian integral, was a sum of 3 terms. One was slow, fast divergence integral, another was just polynomial, and the third term was proportional to epsilon. So again, for sufficiently small epsilon, we can forget about the third term, and so we can just make derivative of n derivative of our pseudo-Abelian integral. So in such a way, we kill this polynomial term. We already forget about the last term that is proportional to epsilon. So this is just n derivative of this j epsilon function. But now we should remember that this is function of argument y to power epsilon, and we take n derivative. But on the other hand, if we calculate this, so it turns out to be essentially derivative of this slow fast divergence integral times some non-zero factor, different from 0, plus terms proportional to epsilon. So again, for sufficiently small epsilon, it is enough to control zeros of this term, but we already know that zeros of this term we can control by integral part of n plus 1 over 2. We need to add some summand related to Rolle theorem, and we end up with estimate like this. But there is, as I said a few minutes ago, there is one more interesting phenomenon, namely argument of this j epsilon function was, let me recall, it is still on the blackboard, it is marked here. So how does it look for sufficiently small epsilon? It's just here we have y, here we have u, and we assume that epsilon is sufficiently small and, of course, positive. So we start with 1, and almost immediately we go essentially to 0. So it means that we have this formula says us that we have this number of canard-like cycles, since essentially this first integral works in very narrow region close to 0 with respect to y. So means that we have canard-like cycles, and the number of these canards is numbers of canards is less or equal than this number, integral parts of n plus 1 over 2 plus 1. And then as we leave this region, so essentially this argument is 0, and moreover, it is clear from the formula for J epsilon function that J epsilon of 0 is 0. So essentially this slow fast divergence integral is switched off, and who is ruled for limit cycles, or let's say such a quotation mark limit cycles, it is this second part that was marked by R, this polynomial. So we have, moreover, n plus 1 cycles that are not of canard type. I would say this is canard far from slow manifold. Let's say it is chicken canards. This number is bounded by n plus 1, and it is function R who detects these chicken canards, and it is, as it should be, it is Dumortier-Ussary slow fast integral that detects canard cycles. And in this case, we can observe all this more or less in explicit way, and this is why I like this example. Okay, so essentially, that's all. Thank you.
Thank you. There are questions?
I have maybe a silly question. What is the motivation for this toy example? Is something historically, or the toy example that you say there?
So motivation was, as I said at the very beginning, we had this theoretical results with Pavao, and the second with Pavao and Dimitri, and the idea was to observe or to construct some example where we can touch this object more or less by bare hands. And that was a motivation.
Okay.
Moreover, the result is even nicer, since we can observe this relation of pseudo-Abelian integral with Dumortier-Ussary slow fast divergence integral, and this split between true canard cycle and pseudo-canard or chicken canard cycles in this case.
But for this example, from this example, is possible to construct another kind of example in this way, or this is like an explicit example that only works?
But what you mean?
I don't know, like a generic example.
Do you ask whether we can modify somehow this example? Okay, now I understand. I was thinking about, so of course the natural question was whether it is possible to just construct a square-like example. So instead of just y, we can take y square minus 1 and x, 1 minus maybe x square, maybe here also 1 minus y square, and somewhere epsilon, let's say here, epsilon. So, okay, I checked this, but, okay, of course you have true cycle here. That's for sure. But unfortunately, you do not obtain direct or explicit formula for pseudo-Abelian integral. Actually, the only way to obtain a really cycle and really explicit formula, actually the same formula, unfortunately is not polynomial. So you should take precisely this example and glue it by using absolute value function. And in this case, really, you obtain precisely this formula and precisely and true cycle. But unfortunately, this example is not polynomial anymore.
I see. Thanks.
I would like to ask you about the relation between epsilon and delta. Delta is much smaller than epsilon.
Yeah, definitely. Even in a calculation, just to underline this fact that delta is essentially smaller than epsilon. In some moment I put that delta is epsilon times delta tilde. Yeah, definitely. Here delta is much smaller than epsilon.
In the straight lines that you pictured, it is important that they are straight lines, or it is just technical?
Well, it is important from the point of view that you obtain a formula. Probably if you replace straight lines by some polynomial, so you can obtain a cycle.
So your proof will pass if you replace by...
Possibly yes, but without such a nice direct formulas. I doubt that. Well, I checked for parabola, for example, and formulas are not explicit.
Just a last question to explain us the difference between chicken and canard.
So canards are cycles that goes very, very close to a slow manifolds. Namely, you can see it on this U function. Okay, it is. I was cheating a little bit here in this picture. There is no direct splitting. To be 100% precise, we have two results. First of all, concerning canard-like cycle, these red cycles, and all cycles. And the passage from chicken to adult canard is not strict, as it's in usual life.
Can you have a canard who becomes a chicken?
No, in this direction. No, in this direction it does not go, as in the real life. Since for sufficiently small, it is definitely Dumortier-Ussary integral who rules canard-like cycles. So in this direction it doesn't go. Well, unfortunately, that's life.
Thank you.
Can you use, in your toy example, can you use your explicit formula for I epsilon and compute a reasonable differential equation for I epsilon itself, like Picard-Fuchs equation for Abelian integrals?
That's a very good question. I do not know immediately answer. I should think about this. I cannot answer you immediately. Actually, I don't know. Possibly yes, but immediately I cannot answer you.
So I have a question. So you say that delta has to be much smaller than epsilon, but somehow in principle in the bifurcation problem you have two parameters, delta and epsilon, and so you should study everything. So what you say there is, what does it mean that delta has to be much smaller than epsilon, that nothing happens in?
No, that actually methods we use here. So actually, as in our paper, okay. The region that is covered here is epsilon and here is delta. So as in our paper, we cover. No. Epsilon must be positive. No. Okay, sorry. Yeah, it was okay. So we cover some narrow region like this.
Okay. Other questions? So let's thank Marcin again.
Okay, thank you.